All right, so we're probably going to take two or three videos to go over the chi-squared test for independence. And there's a lot here, and I'm going into some detail because those of you that are struggling to find enough material to put into your projects, no matter what's going on with your variables, you'll have stuff to present here. And so this, as we can see in this summary, it's a bivariate hypothesis test. It's called chi-squared test for independence. And it's looking at when you have a categorical variable as your explanatory and a categorical variable as your response variable. And the basic idea for my two variables is we're testing whether the proportion of people diagnosed with asthma is significantly different among the different categories of eyewear. So as you look at my week uh, 15, there we go. I had a brain fart there for a second. My week 15 Python, we'll see that I got it from when we were doing our bivariate graphs with categorical and categorical. I had to have my eyewear categories here as part of my explanatory variable. And then I used this code with my asthma. Here I used asthma code because if we're trying to figure out what proportion of people wear eyeglasses have been diagnosed with asthma, then Python is able to just figure out how many people that wear eyeglasses were diagnosed with asthma and divide that by the total, and they'll get the proportion. And looking at these proportions, they're definitely different. So are these differences in the sample enough that we have evidence to suggest that there's a difference in the population itself? And so what we're going to assume is that eyewear and whether you have asthma are independent. They don't have anything to do with each other. There's no association. And that's what we're going to use our sample to see if we have enough evidence to suggest that this isn't true, to reject this null hypothesis, and instead suggest that maybe this alternative is true, that your eyewear and whether you have asthma are dependent. There's actually some difference in the proportion of people who are diagnosed with asthma between those different categories. So that's what we're heading off to do. And so I start to investigate further what's going on here. And it would be nice to see what these proportions actually are, to compare them and see some of the details. So what I've done here is what's called a crosstab. And so the first variable here will be the different categories that you're looking at. And the second variable, and notice I don't have to use asthma code because it's fine to be formatted. What it does is break out all the categories in this first variable and figure out how many people haven't been diagnosed with asthma, how many people have, and then the total. Because these values, like if I'm trying to figure out, well, what proportion of the people who wear both contacts and eyeglasses have been diagnosed with asthma, I just put 158 divided by 756, and that should be what this proportion is, a little bit over 16%. I'm looking at this crosstab again and done a little bit of extra stuff at the end in order to make these proportions instead of counts. So that 158 divided by 956, that's the 16.5% that we kind of saw as the height of this yellow bar. So this is just giving us a little bit more detail about what's going on as I break out the data set into the categories of the explanatory variable and start to investigate those different proportions. Now, if we had a situation where these two variables are independent, what that would mean is that it wouldn't matter what category you were in. The proportion of people who had asthma or diagnosed with asthma would be the same all the way across. And so looking at this 15.4%, if there was no association at all in this sample, I know there's a little bit of an association in the sample, but I'm just using it to explain what it would be like if there was no association at all these bars were all the way across the same height, the proportions are equal, then these proportions would be equal. And what would they be equal to? 15.4%. Okay. So So that's kind of the assumption, is that the population that this comes from has equal percentages all the categories. That's kind of what this null hypothesis means. So what we're going to do in a hypothesis test for independence is say, okay, let's see what a sample would be if it came from a population where all these proportions were equal, and the sample was just like the population and all the proportions were equal. And we'll see what these counts would be in that case. And we'd compare those counts that we would expect to get if our sample had no association at all, and compare that to the actual observed counts that we see right here. So what would the counts be if it was 84.6% no's and 15.4% yeses all the way along here? Wouldn't be what we got. It's a little bit different than what we got. But what would it be? We'll look at that and then come up with a statistic that kind of measures how far from the expected, when all the proportions are equal, our observed would be. Here's our observed. Okay, so that's kind of what the chi-squared test of independence actually does. And so what I'm going to do here is just kind of look at the proportions of yes and the proportions of no. This is a different way to see it. The reason I'm showing this is they really all look about the same up here. Just notice that the blue is the no's. When I was looking at this over here, the heights were the yeses. And here we're just, all the things are going all the way up to 100%. And the blue represents the no's and the yeses are the reds. And so this width is going to that proportion of the both category that was diagnosed with asthma. That's the 16.5%. That's the height of this yellow bar, the 16.5%. Okay. This is the most common graph to look at when you're doing a categorical versus categorical, and you're kind of looking at, does it look like these things are independent? And what's great about this plot, it's called a mosaic plot, kind of like it was tiles in a mosaic art piece or something, is not only does it give us these heights, same as these two, it goes, the no's and then the proportion of yeses. So here's the proportion of no's is the height of this bar, and the proportion of yeses is the height up here. But also the width of these columns is determined by how many people are in that particular category, the explanatory variable. So not that many people wear contact lenses. Most people in this data set don't wear either contacts or glasses. And what we'll kind of find as we go through this lesson, and we're already at 8 minutes, so I may cut this lesson off pretty soon and just make another video for the next piece of it. But what we'll find is not only are the differences in these heights going to be significant, but also how many people are we using? We talked about in class that the bigger the N is, the stronger your evidence is. And so whenever something is using this very small set, there's just not enough people there to give a strong amount of evidence. You're just not going to get that much just to refute the null hypothesis. So what the actual Python code that runs the hypothesis test is these 4 lines right here. First, we import the package that you need, and stats is what we're needing from this SciPy package. And we have this crosstab table input into the system, and then it does this chi-squared test on that table. And what it gives us is quite a few things. So the big thing that I want to highlight here, or one of the big things I want to highlight here, is this table here. And what this is if really the proportions were equal, but you had as many people in these categories as you actually had, what would the counts be? So over here, we have the observed counts. There were 308 total people wearing contact lenses. 47 of them were diagnosed with asthma. The other 261 of them were not diagnosed with asthma. When I look down here in the expected count, if all the proportions were equal, then there'd only be 47.5%. I'm sorry, 47.5 people that weren't diagnosed with asthma and 260.46 that were. Little bit different than what we see here. Not very different, but a little bit different, right? And so what the chi-square kind of does is it compares this expected table, if there was no association at all in your sample, up to this observed table. And so I want to go through in the next video how those calculations are done. So I'm going to stop here and go through how the chi-square calculation is done, and then we'll move on to the next piece. All right, thanks for watching. See you soon.